Okay, guys, let's get started. Today, our topic is about efficient robotic system. We were very lucky to have Jiaming Tang to introduce his great work. He's now a second-year PhD at MIT, advised by Professor Su Han. His research interest lies in efficient algorithms and system for robotics, for more than large models. He's a great system researcher. His work activation well with quantization received the best paper award at MLCs. Um, Later, if we have any technical question, we can interrupt during his talk. For high-level questions, we can leave it for the Q&A time. I'm very happy because I knew Jiaming since a long time ago. I asked him some questions during my undergrad years. Yeah, so great to see you again, Jiaming. I will leave this
Yeah,
for you.
thank you. Yeah, let me play the.
I
Yeah, so yeah,
Can you
thanks
speak
for the.
a little bit louder? Yeah, because
Okay, hear me?
yeah,
Let me turn on. Okay. Yeah, so thanks for the kind invitation and the introduction from you. Thank you very much. Yeah, and today I'm very happy to present our recent work, VLASH, real-time VLAs via future state-aware asynchronous inference. So let's get started. Yeah, so let's start with the motivation. So we know that the current VLAs models are becoming more and more capable, but however, the robot execution is still very slow in practice. So if we look at many VLA demonstrations videos, they are usually sped up by 5 to 10 times to look smooth. And at a normal 1 times video speed, the robot is typically moving very slowly and maybe with some lags between the perception and the actions. So the reason is that most of the VOA systems use what we call the synchronous inference. So in a synchronous inference, the robot waits for the model to finish the inference before executing the next chunk of the next chunk of the actions. So during the whole period of the execution, the GPU is basically idle and just waiting for the robot to complete its motion. So, and since the GPU remains idle and the model is not inferencing during the robot's execution, the VOA model cannot respond to any environmental changes during this period of time. So as a result, the robot cannot handle many dynamic tasks like playing ping pong or like handle some emergent situations, such as mistakenly dropping an item during the pick and place. Yeah, and here is actually the main drawback of the synchronized inference, which is it limits the robot reaction speed. So we can see the figure below, the GPU remains idle and the model is not inferencing during the robot's execution, which is about 500 milliseconds long. So the VOA cannot respond to any environmental changes during this period of time, and the robot cannot handle highly dynamic tasks and cannot respond quickly to the emergent situations. And asynchronous inference is a promising way to address these problems. So instead of waiting for the current action chunk to finish, the robot can execute the current action chunk while simultaneously performing the model inference for the next chunk of the actions. So as soon as the new action chunk is ready, the robot immediately switches to the updated action chunks. So as shown in the figure below, we can see the GPU is not idle anymore, and both the model inference and the robot execution continue without any action stores, without any stores. So by doing this way, the action execution no longer lags anymore, and since there is no stores anymore, and since the robot switches to the updated action chunk whenever they are generated, the reaction latencies actually can be reduced by 10 to 20 times um, compared to the synchronized inference. And here is a short demo of our method. And all demos are run on the Pi 05 model and on a laptop 1590 GPU. And we can see our method is smoother than the other two baselines. Yeah, maybe I can skip this part. Yeah, for the ping pong playing demo, actually, we think the current bottleneck is the tail operation in the data collection. So if we have a better data collection methods, actually we can make it play better with our method. Yeah, and yeah, so asynchronous asynchronous inference is a promising way, but um, actually it fixes the store and reaction issues, but it also introduced some new problem. So we know while the VOA model is running in the background, the robot and environment can keep evolving during this period of time. So the action chunk we predict is based on the states at the beginning of the inference. We can see in the figure below, and it is actually predicted for what we call the prediction interval here. And however, the actions are actually executed after the model inference. So at that time, the robot state has already changed. So we may call this period of time the execution interval. And when the actions predicted are different from the actions are executed, there is what we call the prediction and execution misalignment, and it can cause very unstable and laggy actions. So if we implement the asynchronous inference in a very naive way by simply switching to the new action chunk immediately, this actually causes very unstable control because there is a prediction execution misalignment here. And for example, in the figure below, the inference starts at the S1, and so the predicted actions are predicted for the interval starting from S1, but are executed from S3. And because the robot and the environment keep evolving during the S1 to S3, the generated actions cause some action jump or the jitter if we directly switch to the new action chunk. And real-time chunking from physical intelligence addresses this problem by the action impending. So it do the impending between the old and new trajectories, which is a very clever and interesting idea. But it also introduced additional runtime overhead, which is about 40% the latency increase. So it turns out widen the prediction and the execution gap and cause the model to operate under a greater state staleness. And actually, this leads to some accuracy degradation in some latency sensitive scenarios, especially with larger VLA models or some resource constrained hardware. And now I would like to introduce our method. And the key idea is to bridge the prediction execution gap with a method called the future state awareness. And the key insight is that although we don't know the future environment after the model inference, we actually know the robot states after the model inference. So this future state is actually determined by the current robot states and the actions that are executed during the model inference time. So for example, in the figure below, the states at the execution time S3 is actually equal to the states at the inference starts S1 and plus the actions during the model inference time A1 and A2. So we can feed the current environment observation and the future robot states to the VLA model to directly generate the actions after the inference delay, and thereby bridging the gap between the prediction and execution. But unfortunately, we found the existing VOA models cannot directly leverage the future states properly. And this leads to some suboptimal accuracy and the asynchronous performance. But we can somehow know the reason is that we found the existing VOA models tend to largely rely on the visual input while actually underutilizing the robot states. So, for example, we found on the Libero simulation benchmark, the Pi-O5 model fine-tuned without the robot states input can outperform the Pi-O5 model with the robot states input, which kind of indicates that the model could largely ignore the robot states modality and over rely on the visual input. So naturally, it doesn't work if we simply change the current robot states to the future robot states. Um, but actually, we found this can be easily fixed by fine-tuning. So for the current VO8 models, deployment always requires some fine-tuning on some demonstration data to adapt to the new environment. So during that period of fine-tuning stage, we can randomly add some temporal offsets to the robot states input and also its corresponding ground truth actions. And at that time, we can keep the visual input unchanged. So specifically, the data transformation is like formula. And originally, at the time stat t, we have an environment observation OT and the robot states ST. And we want to predict the actions from the time step t to t plus h minus 1. And now we can uniformly sample a delta between the 0 and the delta max, which is the maximal inference delay decided by the GPU performance or the network latency. And this time, and now we can shift the robot states and the ground truth actions by the delta times that for each data point. And this delta is sampled independently for each data point. So this can encourage the model to rely on the states input for inference, because we know for the same visual input in this case, there might be different ground truth actions. And the only input difference is the robot states input. So we found this way can work very well for the model and doesn't hurt the VOA model performance in our evaluation. And for this fine-tuning, very naive implementation is to treat each sample as a separate training example. So this implementation is completely plug and play, and we can seamlessly integrate it into the existing VOA fine-tuning pipelines. However, it repeatedly encodes some observation OT for every offset. So there is a room for the further efficiency improvements here. And we know that for all the offsets, they share the same observation OT. So actually, we can design an attention map that can reuse the observation tokens across all the different temporal offsets in one single forward and backward pass. And yeah, as shown in the figure below, we can see the upper left part is the observation, and we can list all the offset branches behind it. And by applying this attention mask and proper positional encoding to the model, this is actually equivalent to independently fine-tune all the temporal offsets at the same time. So we know that for 2 images and the language prompt is about 700 tokens in total, and each offset branch is about 50 tokens, 50 action tokens. So we can train with 5 times more trajectories with only about 20% more computation. And in our experiments, we found that this can actually speed up the fine-tuning stage. And here is a sample trick, a very simple trick to uh, further speed up the robot execution. And this is actually very similar to Figure AI's sport mode on the Helix robot. So once the inference latency is covered, is removed by the asynchronous inference, the remain bottleneck is simply how fast the robot can physically move uh, in the action sequences. So for the current VOA models are usually trained on very, very fine-grained table operation data, like 200 hertz for physical intelligence. So for in the many tasks, the policy outputs are very fine-grained actions, and they are actually uh, far more precise than the necessary to solve those tasks. And similar to the large language model quantization, we can by reducing the precision from fine grain to very coarse grain can significantly accelerate the inference with only a mild drop on the accuracy. So given a very fine grained action sequence, we can group every Q actions into a coarser, a large actions. So intuitively, the robot executes a few larger steps that follow almost the same trajectory, but much faster. And actually, the queue is it can be a non-integer. And what we have to do is to do the linear interpolation to do the resample and makes a new action trajectory to follow the same trajectory. And before showing the evaluation results, let me briefly introduce our implementation details. So we rewrote the Pi05 policy based on the OpenPy implementation, along with a series of optimizations that are common in the large language model optimization. And finally, we can achieve about 30 Hertz inference frequency for Pi05 on a desktop 5090. And our robot platforms are the Galaxy R1 Lite and the robot SO101. And here are the simulation results. So we evaluated on the kinetics and the libero benchmarks. And as shown in the figure on the kinetics, our method can consistently outperform the baselines under different execution horizon and the inference delay. And we also include the synchronized inference with inference delay always equals to 0 as an optimal upper bound. And our performance can stay close to the synchronized execution, even at a large inference delays. And in the libero benchmark, we know it's a simulation benchmark, so the synchronized inference doesn't suffer from the discontinuities and the motion jitter caused by the action stalls. So this makes it a stronger baseline than in the real world setting. And in the contrast, the asynchronous inference operates at a inherent advantage because the state staleness caused by the inference delay. And this benchmarks is to validate that our method can maintain a strong accuracy across different VOA architectures under even large inference delays here. Yeah. And our real-world benchmark follows the small VOA setting. So these tasks are to verify all the methods doesn't hurt the general manipulation capability of different VOA models, and to demonstrate that the asynchronous inference can not only improve the reaction speed, but also the accuracy by enabling the smoother actions. So we can see our method consistently achieves the highest success rates across all the tasks and all the action quantization factors. We can notice that our method is more robust to the action quantization than all the baselines. And on the pick and place and the sorting tasks, our methods at Q equals to 2 can match or outperform the success rate of the synchronized inference at Q equals to 1. And because the Q is equals to 2, so it enable actually 2 times speed up without any accuracy loss. And on the stacking task, this task actually requires more precise manipulation than the other two tasks. So our method at Q equals 1.5 still maintains the comparable accuracy to the synchronized inference at Q equals 1. And our method also outperforms the RTC baselines across all the settings because we know that the RTC has some inference time overhead, and it actually widened the prediction and the execution gap and caused the robot to operate under greater state stillness than ours. And actually, in practice, a quantization factor of Q can get roughly Q times task completion time speed up. So if the accuracy is preserved. So in practice, we can select the largest Q that doesn't degrade the accuracy compared to the synchronized inference. And in our experiments, the Q within 1.5 to 2 can achieve about 1.5 to 2 times speed up without degrading any accuracy. And this is adjustable based on the precision requirements of the task. And here's the other VLA models from NVIDIA. It's Groot N 1.6, and we can see our method can still consistently outperform other baselines. And here I want to show the exact control latency to showcase the fast reaction speed. So on H100, the asynchronous inference can reduce the control latency from 523 milliseconds to 23 milliseconds and achieve up to 22 times control latency reduction compared to the synchronized inference. And on the RTX 1590 and 4090, we can achieve about 18 times and 16 times latency reduction, respectively. And this low latency control is very essential to the highly dynamic tasks like the playing ping pong and playing whack-a-mole. And we can also use this to do the high frequency correction for the VOA model and the robot execution. And we also evaluated our fine-tuning efficiency speed up of our shared observation method. So we compared the original standard fine-tuning method and our method with the shared observation optimization. And the delta max is set to 3. So the delta is sampled within 0 to 3, and the effective batch size is 4 times larger than the physical batch size. So with the 64 expected batch size, we have only 16 physical batch size. And the standard fine-tuning still has 64 physical batch size. So we evaluated the libero scores at different training steps, and our methods converge more slowly in the early stage because we are the future state aware. So we have to train a different delta. So it converges more slowly at early stage. But finally, we can achieve a comparable accuracy to the standard fine-tuning. But we can also achieve the 5 times speed up per step. So eventually, we can achieve a shorter end-to-end convergence time. Yeah, and here is our code. Our code is published and released. And this code base is an efficient and easy to use framework for VOA fine-tuning and inference. So it can support the robot data set seamlessly. And it also supports asynchronous inference for faster reaction and smooth motion. And we also support action quantization and LoRa fine-tuning on the custom GPU. Yeah. And here is our presentation. If you have any questions, please feel free to ask. Thank you.
Hi, Jiaming, I have a question. So you fine-tune the base model for each task. So how much data do you use for each task, basically?
Yeah, for usual deployment, we usually collect about 50 to 100 episodes, and that's enough for our method. Yeah.
Do you require the teleoperators to control the demo speed?
Oh, it's not needed. Yeah, just performing just teleop in the normal speed. Yeah.
So,
Then we can do the speed up with action quantization afterwards. Yeah.
do you think the upper bound of this asynchronous inference is the demo speed, or after the speed up, the speed can pass the demo speed?
Sorry, like to the asynchronization for the synchronized inference or?
Yes, yes.
Yeah, I think the main improvement of asynchronous inference is the reaction speed. So it dramatically reduced the inference the reaction speed from about 500-ish milliseconds to 20-ish milliseconds. So I think that's the main improvement compared to the synchronized inference.
Yeah, I mean, after the latency, reducing the
Mhm.
latency, the
Mhm.
overall execution time is shortened, right? I mean, so the overall task execution speed, can it overpass the demo speed?
Oh yeah, yeah.
That's it.
That's the main that's the goal for the action quantization. Yeah, so we can pass the demo speed.
That's it.
Uh, I wanted to ask, I was curious, um, how does the method handle unexpected inputs that happen? Like, okay, so for in one of the demos, you had this like point game, right? Where the goal was to click these flashing lights. What I don't get
Mhm.
is, like in this method, if a light happens after I've already predicted the actions for the if the light appears after I predict the actions for like when my hand is going to move, how does this method like handle moving the arm to the correct place, even though the light appears after I've already done inference? If that makes sense.
Yeah, because the inference is performed in a very high frequency, like 30 hertz. So it percepts the environment like 30 times per second. But the lights flash for about 2 to 3 milliseconds. So it's okay to do the high frequency correction for that.
So I guess like in general, it's for the general form of this problem where like something happens after I've already made my action. The
Mhm.
solution you guys are rolling is just like, well, we'll make our inference so fast that we can always react, even if we've already made like, yeah, okay.
Yeah, yeah, yeah.
I think there's a question in the chat.
Yeah, okay. Uh, I didn't see the questions in the chat.
But, oh, sorry.
Thank you.
Yeah, sorry, I have one last question.
Mhm.
So right now you fine tune you decide the action quantization coefficient for each task. Uh,
Mhm.
so do you think uh, do you think your method can work on multitask fine tuning? Because let's imagine one task has very uh, fast speed requirement, or another task in contrast are not.
Yeah, actually, we have tried that. So we trained the playing ping pong and pick and place and like the three manipulation tasks within one model. So it works because the fine tuning stage is like teaching the model to adapt to the like the prediction and execution misalignment and teach it to leverage the future states. So like it's not a problem for the model that it has to perform the highly dynamic task and the generate general manipulation task at the same time, and it's okay. Actually, if we have more data to fine tune the model, it performs better. Actually, yeah.
I see. I see.
Yeah. Mhm.
Sorry, this wasn't like completely clear to me. I'm sorry if you mentioned it, but I don't get the why shifting the states and the actions both works, right? Like during
Mhm.
inference, supposedly we don't have these teacher states, right? But I mean, we have the current observation, but we don't have future states. Like, what? How does how does it still work?
Yeah, actually, we can get the future states during the inference because now we have the current robot states, and we know we have the actions that will for inference time. So we just add up the current robot states and the future state we are to execute. Then we can get the future states,
I see.
but we cannot get the future observation. Yeah.
Yeah, I have a question. So basically, we assume we are not under any perturbation, right? Otherwise,
Mhm.
given the current state and the action, we cannot predict like the future one because that one can totally
Yeah.
already. Yeah.
Yeah, there can be actually small errors between the actual future states and the estimated future states. The model can tolerate that. Yeah.
Yeah, but I'm saying like that's because maybe our task is more about the bimanium, the tabletop, something that
Mhm.
is not highly dynamic. For example, imagine like a robot, like a
Mhm.
humanoid robot, and then you drag like the arm like on
Mhm.
purposely. So you will definitely change like the future state because you don't know what the output from the user side, from the environment side. So under that
Um,
scenario, do you think like this method can be improved in some way, or how we address that?
yeah, actually, I think the playing ping pong demo is kind of dynamic.
Yeah,
So
but
at
but
that,
but that
yeah,
one, yeah, but I think that one is like we always hit the ball at a certain time range or
Mhm.
or a certain pose. Like we never hit the
Yeah,
ball at some other pose. So that can also be predictable if that is repetitive.
yeah. I think if the actual future states is way too different from the estimated future states, then that definitely would be a problem. So so that we need to estimate the future states as accurate as possible. So within a certain range of the error, I think is tolerable. But if too large, then I think there will be a problem. Yeah.
Yeah. I totally agree. And I really think this is a good starting point. But my question is
Mhm.
more about um, like for you future work, like will you keep using this framework or you just like release that and move on? For your next project, you won't like always do the fine tuning to
Mhm.
make the action more smooth because you also might aware some like some limitation of this method, where you will keep using that because you feel that's the right way uh, to really improve the control.
Yeah, actually, physical intelligence recently has a paper very similar to our paper, and it's called a training time RTC.
Oh yeah,
And
artist. Yeah.
the main difference is that it just fine-tune with the like the action chunk that will be executed. And actually, these two methods are very similar in principle. And the main difference is to fine-tune with one state or a sequence of executed action chunk. Yeah. So I think for the general manipulation, like the main task of the current VOA models, I